So I'm truly delighted to be here, and one of the reasons for that is, and I made a little map here about like where I'm coming from. I'm really a true child of the 22nd district in Vienna. I grew up in the 22nd district. Everybody in the audience knows how that's called. That's Transdanubia. So I started in Transdanubia, and I just want to show like a little stations of my Viennese life. So you can see on the left side the Gymnasium Polgerstraße in the 22nd Transdanubian district. I've spent a lot of time at the old Danube, mostly rowing. And my first job, actually, to kind of like finance my studies was in this very little, in this very little kind of like, oh my God. Okay, sorry, there's something going wrong. So it was in this very little cafe that you can see there where I was actually a waitress, and I was kind of like earning my money in my studies and kind of like giving out schnitzels a lot. And then I also earned like, and that was the second part of my career, my money being like a science writer for the Austrian newspaper Die Presse. And there's like several articles that are actually from when I was about like 20, 21, where I wrote like about different science ideas that were going wrong in Austria. So I'm very deeply connected actually to Austria and the 22nd district. And that is why I'm really honestly very delighted to be here today. So now going forward, where did I go? So I came from the 22nd district and I did my PhD at ETH Zurich and then hopped for a while afterwards for my postdoc in Japan. And then actually moved back to MIT, and that was my first time when I started there for a second postdoc, joining MIT in the material science and nuclear science department. And then short after, it took me back again, and I did this really weird rotation where I went from MIT postdoc back to ETH to become a professor, and then back again to MIT and being snatched away actually by the MIT folks going over there. So that's a little bit about my journey and about my connection actually to Austria. And today I work with a number of companies. I just want to highlight that I'm 95% industry funded with my research at MIT. So I have really this deep desire to give back to society by not only publishing what we do in the science, but also like really working with companies and thinking about how can we give back quicker to society in innovation and actually support them in translating different things that we do also later to products. So with this little introduction, I would like to kind of like talk a bit about why we do this research actually in energy and information data. So if you think about it, the evolution of our society is deeply rooted on the fact on how much data we can actually transfer, compute, and process currently. And that is not only, I think, about like how much data density can we process and actually translate, it's also questions about like what is the energy consumption that is correlated to that, how much in budget, not only in finances, but also in energy, will these processes cost us? And they have a deep impact on our life. So if we think about it, there has been different revolutions in the human mankind. So if we think in the very early ages, then actually the steam power was the first industrial revolution. And the second industrial revolution was actually connected to everything you can do into mass production and actually translating to work. Now we are since the 70s in the so-called kind of like start of the first industrial digital revolution, where with the birth of the transistors, we could actually enter a new era where we can compute data. And the so-called fourth industrial revolution that is starting is actually the interconnection on how the data impacts the life, not only by computational power alone, but for instance with sensing. And there would be multiple examples alone already in the room right now here, where you want to have feedback loops and you want to actually enter the era of artificial intelligence, or where data can be suggested to optimize algorithms and functions later for different types of products. So if we think about it, the fourth digital revolution is not only about computing data, it's this connecting network that you have between data computation and then later sensing functions, giving feedback loops on the era of our health, on the era on our energy consumption. So it's actually something that is not only restricted to having small gadgets, that's what a lot of people think. It's really actively giving you, for instance, a better life perspective because you have MRIs or different feedback loops that can measure your body, and you could, for instance, become more healthy or prevent diseases. So this is, I think, some very deep reasons to actually care about what is going on there. So just to give you some examples where you can see that there is like an imminent kind of like network, and it's not only about algorithm, what's happening in the fourth digital revolution, but it's also an interconnection between hardware and algorithms that are used, and materials are quite relevant in that. So if you think, for instance, about future digital textiles that could prevent diseases, then you need to have different sensors on these textiles that can measure your body functions and that can give a feedback loop to a little processor unit that you would have in a smart textile that could tell, for instance, you or your doctor or anybody else how you're currently like in your well-being. So there needs not only to be the algorithm to read out all of these new functions, but also later the hardware that is even able to process, or in case of a flexible textile, the material that would be soft, so you don't want to go with a hard plate, right, of silicon around you. So there needs to be actually some real manufacturing that is going to join actually this next challenge. And that goes, I think, in a very intertwined region between new materials, new sensing functions, controlling the energy amounts that you have, and having the computational power to move away from traditional computation with algorithms and hardware. And I have here one picture that you can see that is currently, for instance, the Google data storage. And if we look into that domain, then it's very driven by transistors that we have already since the 50s and 40s. So the only thing that has happened in computational power over the last decades is that everything just became smaller. And to give you an example on how a transistor works, I have here a little sketch on what I mean by a transistor. So a transistor is a very simple silicon device where you have like 3 contacts and you can modulate an internal resistance by applying a bias. And if you look on the right side, you can see an example of a silicon wafer where you see a lot of transistors that has been processed. And the reality is that since the 50s and 40s, the whole technology on which we compute, and that's quite fascinating, hasn't changed a bit. It just became smaller and smaller and smaller. So we increased the density. The challenge is here that with the classic transistors, you are kind of like physically dependent on the modulation of an internal resistance value. When you apply, for instance, a little voltage, you can set a resistance value to a new state, and you can manipulate this transistor in going between 2 different resistance states, which gives you later a binary coding, which is normally referred as a 0 and a 1. And so the whole algorithm with which we work here hasn't changed over the last decades. It just became smaller and smaller, but it's actually all the same technology. And when you look on the screen here, and as you're really good Viennese, I know immediately that you know what actually is written here right now in binary coding. So it's saying the Austrian sentence, in meine Darm, da steht der Baum. So which means in English kind of like there's something in my way, right? So that's actually the binary code for that. And if you look at that, even if I translate this Austrian sentence, then this is actually like just a number of codes and zeros and ones. But it's actually very far away from the way we would love to compute, which is not in binary coding. But I will get to that actually also in a minute. So where has that all started? So when we look in the history of transistors, then the first transistors were very bulky setups. And you see here actually one that I copied from Lilienfeld, which is just like a piece of hardware. And I just put it there to demonstrate to you it's all about hardware later, and not only about algorithm, where you have actually all the contacts of a transistor, but a very bulky, shapy type of device that you see here. Now, where the evolution has happened is really later that the one sketch that I showed you is actually to bring all these structures down on silicon by doping different entities and making actually a device where you can later do the resistance state switch. And that's an example of a classic transistor chip where you have today a decrease of the size from the device you saw from Lilienfeld before, which was something like in the centimeter range, which is going now to about 14 nanometer in range. So you have to think about it, your hair, if you grab one out, you can just all try it would be fun to see that in the audience right now, would be something like on the micron scale. So this is still like a factor of 1,000 smaller when I talk about 14 nanometers. And that is the classic shape that you have transistors today. So it's very difficult to decrease that actually any further. And what's the impact of that? So the impact is that if you think about computers, it has very largely to speak about like what's the information density that you have available. So on the left side, you can see, for instance, from the 50s, a first supercomputer that was not using the silicon transistor chip, but more other devices like the other one seen before by Lilienfeld. And you can see these all around of the switches there, and you have actually very low information density. On the right side, you can see, for instance, one of the current Swiss supercomputers, and I took the next neighbor to Austria, which is Switzerland, right? And you can see there actually that there is a stronger increase in the information density that you have available to do later computation. So actually miniaturizing the overall transistors here is the key, for instance, in hardware to later have an evolution in being even able to do more computation. So there is a so-called Moore's law, which tells you about like how much calculation power do you have per second for about $1,000. And you can see here over the years that there is a strong evolution which goes directly with the hardware that has been fabbed on. So we are currently at a node size of 14 nanometers, and physically it's not possible to make transistors any smaller because you come into restrictions where you can't actually modulate these resistances any smaller. So you have to think about an atom. It's like only a factor of 100 smaller, so the society has come quite far, but we can physically not break those laws that are available, so we can't really go any smaller than right now. So one point to move away from transistors, and that's the why on why do it, is actually first of all that we're limited by Moore's law. We can't go smaller. And the second factor that may sometimes not be known to a lot of people in public is that when this computer is running, it's very inefficient. You have some areas that are working with a high heat and others on the chip components that are actually at a very low heat. So you have not a well-balanced energy balance in the overall computer, and that's what's sometimes called the dark silicon, which uses a lot of power. And that comes really also from the geometry of the transistors, different physical constraints, and that costs you also in terms of calculation a lot of energy when running, for instance, this notebook right now. And the third part is that the binary coding and also the way we have actually transistors right now doesn't allow you to process information or store them at the same time. So this computer right now has to decide whether it's going to process information or store it. That's the so-called von Neumann bottleneck. And with that, the binary coding is coming to a very limited end, so there needs to be alternative if we want to go in an era of the fourth digital revolution to find alternative hardware and physical principles to do more in our computation. I just want to throw in here some numbers on what is the impact. We can see here, for instance, the evolution actually on the Internet of Things, and what is meant by that is really the interconnection that you have actually between that hardware and the computational power, and for instance, sensing a smart home. So it's a gigantic market, and also there is like a strong vision on sensors and the evolution actually, which is going also in a trillion sensor per year that is going to be produced actually up in the next 5 years. So it's going from 1 billion to 1 trillion. So the interconnection becomes quite important, but we are limited in the hardware that we're having right now. So one way to solve that could be quantum computing, but another way which could be much easier is so-called memristors. A memristor is physically a very simple device, which is in German a so-called Kofferwort. Yeah, I didn't know this word either, like some years ago, but Kofferwort means that it's a word that is kind of like a mimic of two words. And it's something that comes from memory and resistor. It's called a so-called memristor. And a memristor is a device where you can see that when you have a metal line and you have an oxide material component and a metal line on top, it's a quite simple structure, and you make thin films, then you can observe that at very high local electric field strength, you have a hysteretic current voltage profile. And the only thing I want you to remember from it, that some of you may remember your physics textbook where you could see a straight line, which is an ohmic resistor, which is actually what you have between a current and a voltage normally. And I tell you now, if you make it small enough, you can see a time-dependent response of such a resistor. And if you see that, because you love to do kitchen physics when you come home tonight, that's a memristor, okay? So in a nutshell, that's what you see here in a memristor, and it works by the fact that some of the metal oxides have actually some accumulation and depletion profiles of charge carriers at interfaces. And if that's happening, you can observe this time-dependent so-called memristive curve. So why am I truly excited about that? The first reason is that over the different derivatives of this curve, I can assign more than one state. It's not anymore binary. I can have multiple resistance states, and I don't have to code anymore in a 0 and a 1 like the example I showed you, but I can have like many states in between of that, and I can use those for computation. So in one volume where I had before 2 types of information, 0 and 1 that I compute with this computer, I could have 1,000 or 1,000,000. So that's actually very attractive because you know the word bit maybe, which means binary information. You can kick that out of your vocabulary. What is coming is that 1 unit could have 100 to 1,000 states. Where that's also quite interesting is that if you think right now really hard to follow my lecture, then your synapses fire in your brain. And the synapses are strongly ionic systems, and you have little potassium and calcium ions in your synapses that just like walk between your synapses. And they have a similar high density than how you can process currently these memristors on a chip. The other exciting part is that both of them are ionic systems. So in a memristor, you have also mostly ions that are actually making in the oxides this modulation. And when your brain thinks right now, you have a similar type of ions that is firing in your brain. So there's, let's say, a lot of similarity between the physics of a memristor and how the brain of a human actually works. And one can use that, and so also when you think right now, you have not a binary system, so your brain is capable at each connection point of a neuron to make like also 1,000 or more states actually of different information on a similar spot size. And memristors are a similar way where you can actually bring up and have a similar density of information than what you currently are capable to do in your brain and process in a similar way. So where's the challenge right now with these memristors? So it's a quite young field. It came first up about like in a proof of experiments about 10 years ago. But I always like some good science stories. And the story to this one is that the theory of a memristor was already existent in about 1972. Now you may look actually at this drawing that I scribble here, and it may look like really funny lines, right? So it looks very artistic. But what I want you to take home from this is, and that's just like where I think you may know some of these devices, is that there is a correlation between current and voltage and time. And that is defining in physics whether a device is later a resistor, an inductor, or a capacitor. And Leon Schur in about 1972 was a theoretical physicist. And he actually found out that there could be a time-dependent memristor. So he kind of like wrote up the whole mathematical theory, but it took about like, I think 40 years until the first memristor was actually made by Hewlett-Packard, showing the functionality that you just have seen here below. And what we all like about it, where I think it is more powerful than quantum computing potentially, is that it's a very simple architecture and structure how it works. So coming back, actually, what's going on in these memristors and how do we have to understand it? So on the left side, you can see an example of neurons in the brain, so where you can actually see here neural connections that you have here, and you can see the firing between these synapses that you have when you transfer information. So you have little voltage pulses, and they are controlled by a flux of potassium and calcium ions. Now in these transistors, the most simple transistor architecture is to use a material called titanium dioxide. It's a small ceramic coating. And in this material, for instance, you can accumulate and deplete charge carriers, which are oxygen ions, at interfaces, depending on a bias. And if you go at very high local electric field strengths, you have actually this memristive effect, which is actually a similar time dependence than what's the neurons do actually in the human brain. And the thing gets very complicated. So what we do currently at MIT on a lab scale is really build this type of artificial synapses by memristor structures. And you can see that on the left side, where you have an intersection of two metal lines with a solid state oxide material in between. But if we think on where that should go, it is later like to mimic what is in the biology actually on a chip as a hardware. So it will at some point really go from synapses to microcircuits of these artificial synapses made by memristors. And of course, there is like this sci-fi vision that at some point that would go actually to mimic larger, very complicated structure like the brain. So just to tell you the truth, we're not there yet, right? So we're just like still on the first 1-2 parts, but we're trying at least, to go there. And I think this is actually pretty exciting times that we have materials and hardware that can do that. What else can one do with so-called memristors? So memristors can not only be used to do what we call neuromorphic computing, so mimicking, let's say, brain processes and learning and forgetting, for instance, in circuitry like we saw it before, but they can also be used, for instance, as different memory media. So if you think about it, I'm sure all of you have a USB stick with you, or most of you, and you may also have like a computer. So your computer is working on transistors and has a DRAM. And your USB is actually a flash drive, which I just put up on this little sketch to the right. And memristors have about a 1 order of magnitude lowered voltage to store information, and they do that non-volatile, which is superior to flash and DRAM. So if this computer is working right now, it needs an energy pulse every 64 milliseconds, right, to activate and keep this information. So a memristor wouldn't have that anymore, which is also in terms of the energy balance quite attractive. And currently in US, there is a whole nuclear plant only working on the standby of all the non-switched off electronic devices. So I do really see a very imminent impact between energy and information. So we have also as a society to consider how much are we willing to spend on that, and what is acceptable and what not. And memristors here have a very high perspective to really contribute in reducing the energy cost per information transfer and storage. So where's the field right now? So I mentioned it's a quite young field. It's about 10 years. But I want to mention that there's first actually things on the market that you can buy. So you can see on the left side a Panasonic microcontroller, and then on the right side an industrial memory. And these type of devices right now are actually working on memristors and are using this technology quite actively. So even though it's a young field, in the field there's an immersion connection with industry, and it's really up and rocking. And I think you will see probably in the next 10 to 20 years much more memristors in all kind of devices, and the transistors going down in terms of hardware. Now I want to show you a first example that's coming out of my lab. So one thing that I thought some years ago, which is really attractive about memristors, is that unlike in a transistor, you're not limited in hardware to have a silicon wafer where you later process your transistor structure on. And the problem in those is that you always need to have some doped regions. So it's very difficult to stack transistors kind of like in the third dimension to towers like little skyscrapers, where you would kind of like gain a very high information density. So there's like several physical limitations in doing that. In a memristor, the beauty is that you can stack like a little New York tower, like hundreds or 1,000 also in the third dimension. So you can see here you have a metal line, an oxide, a metal line, and it doesn't stop. You could just like continue in the next level and bring many of these information densities together. And at each cross point that you see here on this little star that we manufactured, we don't have a bit anymore. We have like one memristor unit which can compute up to 1,000 states, and we just stacked the next unit just on top of it. So it's fairly easy to make actually very high information densities of these so-called memristors. Now I want to pitch your brain on what I'm most excited about in the last year, I think, yeah. And coming back to my argument that actually power and hardware is also immersely connected to resources, and also on how much energy do we want to spend in, for instance, neuromorphic computing. And I want to talk here a little bit on a larger perspective. So if we think about it, a lot of you are currently driving a car, and I don't know how many Tesla drivers are here, but think about it, you have a set of materials later in electrification of cars in the battery later, and the material currently is only used in the battery. If I look on a phone, then I have in my phone currently a battery in the back end, and there is a processor maybe somewhere, and there is some sensors in that phone, but it's all different units. So think about it, what if I tell you that there could be a world where some of the materials that you use in the battery don't need to be useful for the battery anymore alone, but they could also be sensing your environment, or the same material could also later become a material that can compute. What is if your battery can compute? That would be pretty cool, because we would reduce the share of resources and add more functionality to materials and devices. And I think it's something that is really worth to think about, and I want to give you an example. So you see here a little, it looks like a very grayish, scientisty sketch, I do admit that. It's actually a material which is a very fast lithium conducting thin film, and you could either use it later in a battery, but you could also use it to have other properties like being a memristor. And I recently postulated that similar materials that are used in batteries that are very fast conductors, so they can transfer lithium very fast, so you could ultimately use those later in a battery for a car to have fast charging and drive your car without any fuel, so that's great. But you could use the same material class, because it has a very fast flux, to also compute data in a memristor or sense your environment. And I think it's very important, because we want to use less resources and materials. And if you're a manufacturer, you could have already a line on batteries, or a line on neuromorphic computing, or a line on sensing, but you could add more products with the same material that you are kind of like offering. And how that works is kind of like you have a fast lithium-based base material, and depending on the electrode set that you're going to use later, you just redefine the function to be a battery, be a sensor, or be a memristor that we have seen before. And it actively works, and what limited that so far in material science is, on the materials available, is that we didn't have very fast charge flux conductor for ions, but there's up and more materials coming up that can do that, and where you can design actually new electrochemistry to pursue that. So coming back to the memristors and the question of energy, I want to make the following point. So the HP memristors that you have seen before from Hewlett-Packard are mostly working on the motion in the oxide of oxygen, silver, or copper ions. And as a material scientist, I must say this is not the fastest motion of ions in materials. So if we would go, for instance, to lithium that we know from batteries, we can gain orders of magnitude in computational speed. So you would be much faster later in your neuromorphic computation, and you would use actually the same type of materials. And there has been some very recent exciting work where, for instance, a classic cathode material that you can find in the Tesla car. So this is the lithium cobalt oxide. That is the cathode you have in the Tesla battery. And the same material can actively be used, and you can see that on the right side, to have a similar funny-looking computational curve, which is again the so-called memristance. And when we saw actually that paper, we were quite impressed, because that means that you can give it an additional function. So what has been before your electrode and your battery of a Tesla car could become your computational unit in the next 10 years. And that's quite important because you give the material more functionalities. So looking into that, my team thought, well, that's fantastic, but actually in terms of energy efficiency, that's a material which still needs a very high voltage, so it's not the best choice actually to use this specific one. So what we kind of investigated is actually to take some material which is lithium titanate. It's sometimes used in anodes of batteries, and we can process that as very tiny thin films, as you can see an example on the top right. So it's actually about 400 nanometers thin film, so that's a factor of about 10 smaller than your hair that you can rip out again just for me to see the effect, right? And if you do that actually, then you can see later that you can also bring that on a chip, and you can see in this very simple structure again that you see this hysteretic current voltage profile, which is a memristor. So this is the very first lithium titanate memristor that has so far ever been published. And the exciting thing about this one is that it has very high and great characteristics to do computation of data, so we can loop that for several days. We can compute data similar to what your human brain is doing. Now, looking into that, we were thinking and asking the question, well, if it's all dependent on some carriers, what is happening in the material if I modulate the base state of the carrier? And that's very difficult to do because a lot of these materials that have been used in batteries you can manufacture them in a very big way. But if you want to bring it on a chip, and that's later where our computation is happening, it needs to be a thin film. And I have to come back to my dimension of being just an order of magnitude smaller than your hair. So that's actually very difficult to do because currently there's not much manufacturing skills in industry on controlling how much lithium is in those films and actually having those very high concentrated lithium films. So we did some manufacturing invention where we placed a lot of IP and where we could actually show that by alternating, for instance, in our processing an extra layer and doing some decomposition reactions, this allows us to make very precisely controlled lithium oxide material films, and that's quite needed later to control for computation how much of the carriers are later available. And the really exciting thing, and I'm not truly excited about that, but I will break it down for you in a nutshell what that means, is that depending on how much carriers we put in these materials, we can have this left or the right butterfly curve. And you can obviously see they look quite different. So one is very asymmetric, the other one is very symmetric. And that is very important later in developing algorithm by hardware, because the left side would be, for instance, very suited to mimic your brain in neuromorphic computation, whereas the right side is perfect to make in your memory. So far, a lot of our materials and computation can do either the left or the right side. And a classic transistor that cannot switch in the outcome curve, so it's difficult to adapt the algorithm for that. So what I'm showing you here is a new material that can be on demand triggered by processing to do either the left or more the right side in performance. And that's quite important later as material scientists to develop and work together with electrical engineer to have the hardware ready to do these different type of computation. So what we're currently working on is a device that is called Lister 2.0. And it's actually a device where we can control a synaptic weight that you have in your brain. So your brain can either, for instance, decide to go on the left or the right butterfly curve by how much potassium and calcium is shooted in a certain time range when you think right now hard to follow my lecture. And we can modulate that by coupling a so-called Memristor device and setting on top a little micro battery where I can pump lithium in and out, and I'm suddenly in control on what my brain does actually on the synaptic weight. And such devices are almost not existent right now, so there's like just a few concepts around, but it would allow later for an electrical engineer on demand to kind of like allocate how the output algorithm can just be simply adapted for whatever process he has. It's very energy efficient. It's a very fast flux motion. And what has been so far in your brain, the potassium and calcium running the show, is here actually done by lithium. And what has been a traditional battery is not a battery anymore. What has been a traditional memory or computing unit is not a memory computing unit anymore. If you bring the two together, you have new type of Twitter devices that can do so much more. So your battery can suddenly compute. Or it could also sense something. So it's actually very, I think, exciting new times that are coming up. So just in a nutshell, to wrap up, what I'm currently quite excited about is actually that there is an era of new crossing over devices where we give more functionalities to materials, and that's quite important in the vendetta and the race with having actually neuromorphic computation, not only, and that's something very important to me, as a cost to be very cheap for manufacturing and industry, but also to be socioeconomically aware to make products that are later affordable and not restricted in their elemental use to some countries only being in charge of elements, but to have a wider spread. So I think it's quite important that researchers and industry work here together and work on these new Twitter concepts. So I come to the end of my talk, and I want to thank you very much for your attention, for the kind invitation to come back to Vienna. And of course, I want to just leave you here with an impression of a not so serious MIT group. That's my team in the elevator going up for lunch. And I want to thank you very much for inviting me here to Vienna. Thank you.
Okay, so we have lots of questions. What are the challenges to manufacturing memrisistors on an industrial scale?
Yes, that is a very good one. So I think currently it's like endurance. So it's endurance and retention. So that's later what the device has to perform. So you want to have a memristor that you can operate for 10 years and keep an information state for 10 years. Now to do that, you're fighting leaking currents in your architecture that you have on a chip, and that is still a challenge in industry. So finding, as material scientists, strategies on how to predefine where these different ionic channels are going to form in the material is the key, and there is different concepts around currently.
What is your feeling on the time, money, and collaboration that it will take to get from memristor synapse stage to the neuron stage and further?
Mm-hmm. I would say that on the neuron stage, I think it is there, so it's grabbable. So I think it's something like maybe five years. It's not very far away. I think later to do very complicated computation and self-learning networks with that would take far longer time. So depending on the time and money, that's always a difficult question, but I would anticipate the industry I see right now with that to take easily another like 10 years maybe to develop that further.
It says, by the way, bit, and I'm looking at Kofferwort aus English binary digit. What about MIT? And I see Kofferwort aus multiple digit.
Can you repeat that? I don't have my glasses.
It's a Kofferwort.
That is brilliant. I only can comment that is the thing where I will literally sit on a plane and just think about how to bring that into my next talk. So whoever that's Daniel. So Daniel, let's have afterwards a drink. That sounds great, terrific. Yeah.
Are memristor bits even more powerful than quantum bits?
I think that's very difficult to say. I believe that it's very important that both directions are developed. And what makes later the race, and there could be different applicational use cases, is very difficult to predict. And again, coming back to resources, that will also play a role. Like what type of resources are needed in terms of elements for the one and the other later. So there's like not only the tech factors, there's also a socioeconomic factor in that. And that is something that's quite complicated to predict. The best thing we can do as MIT is inform about where the technology is, what it could do, and then go into discussion with economists and politicians and see where that goes.
Can you describe the difference between, I guess it's qubits and Memristor? Do the technologies leverage each other?
I'm not myself working into qubits, so I kind of like charmingly go out of this question to not answer like how exactly a qubit works right now. Therefore, I think it's difficult for me to answer this question right now. I would leave out of this question.
How do the current investments in 7 nanometer technology match with your statement that we have reached the limits of 14 nanometers?
Right, so I think currently like 14 nanometers is what you can find. So there is, for instance, roadmaps by the semiconductor industry on where they are and what they predict next, right? So with investments, it will probably maybe also go to 7 nanometers, but at some point, look at it. You have to, I mean, we have atoms, and that's the smallest unit you can build materials with, right? So if you have later a silicon wafer piece and you have a doped region in that, you cannot go smaller at some points than atoms. So at some points you come in a natural limitation. And so I think the other factors like the von Neumann bottleneck as well as the energy consumption of that are quite difficult. So I believe that therefore, yes, there could be that it maybe goes there, but it's very limited in holding up with AI and doing all by transistors. I don't think there's a very high perspective. Mm-hmm. But it's an established industry, so it's there. That's already a good part, right? Yeah.
Do you and MIT hold patents that are ready to be licensed?
Oh yeah, I have a whole portfolio. So one of my big reasons, and I want to make a big compliment to ILP, why did I move to MIT? I could have stayed in Europe. One reason is that I understand my team not only as being scientists, but also inventors. So alone in the last year, we have a lot of IP in Memristors and on energy technology. If you want to talk to me for licensing, very happy to do that. We have several companies with who we work, some of the patents that are jointly filed or licensed. And the situation and having the liberty and also the support in doing that at MIT has been just enormous. It was for me one of the most exciting rides of my life so far. And I'm very happy actually that I have all these opportunities, and I'm very happy to talk about that.
Yeah.
Yeah.
What do you think of storing data in DNA as explained yesterday? That was a company that was here.
Yeah, I think it is very exciting. Of course, it's like soft matter. So what I talked about today is hard matter. So maybe you can see both talks in joining in material concepts and how to store information, where one is working on soft and the other one on hard matter. And I think it's very synergetic. It's just like different types of elastic modulus you will have in the material building blocks, for sure, yeah.
And our last question, if the constraints of the old transistor technology are already reached, why has the disruption through new technology not happened yet?
That's a good question. I think it always takes a time until actually the new industry also in manufacturing is ready. What I observe, and that's a challenge, I think, in Memristors, but also for instance, energy storage, is that very often when you have a new trend, it's very fastly ready by the scientists to have a physical concept to explain it. But then to have the manufacturing ready and support active the industry normally lags behind. So let's say if you have like silicon technologies, it's obvious there's like decades of industry prepared for that. If we come now with Memristors, well, that could be integrated, but still the oxide hardware part needs consideration. And that's, I think, like taking a lag behind. So it's always leaking behind, but that's something where we try to do an active job and working together.
Well, Jennifer, thank you very, very much.
Yes. Thank you very much.